Hello everyone and welcome back again to another math video. So we just finished with differentiation. There are maybe one or two more sections about implicit differentiation and second and higher order derivatives, but we will not cover those on this channel. Yeah, you can just read up on them. But in this video, we will jump straight into the next section of calculus, which is integration. And I'm sure you've heard a lot of things about this. Some people say that integration is like the opposite of differentiation, which is true to some extent. Some people say that an integral says something about the area underneath a curve, which is also true, again, to some extent. So in this video, we won't actually learn any integration techniques, but we will just talk about what it is so that you get a solid understanding of what it actually is before we learn about any techniques, which will come in future videos. So the first thing we should talk about is the difference between definite and indefinite integrals. Okay, there are two types, definite and indefinite, and they are different. So the indefinite integral is pretty much just an antiderivative, okay? And I'll show you what that means. Let's say we have two functions, f of x and g of x, and one of them is the derivative of the other. So let's say that g of x is the derivative of f of x. So if we differentiate f of x with respect to g of x, with respect to x, we get g of x, and we can write that as f dashed of x equals to g of x. But how can we write f of x in terms of g of x, right? And we do that with an integral, okay? And that's the sign for an integral. And we can draw our little arrow here to symbolize integration. So integration is the reverse process of differentiating. It's like subtraction is the reverse of addition, division is the reverse of multiplication. Differentiating is also an operation which we can undo by integrating. So if the derivative of f of x is g of x, then f of x is the integral of g of x, okay? So it's the reverse process, and we always have to add a dx, okay? And the function of this dx here is to tell us that we're integrating with respect to x. Okay, so for example, if it was g as a function of n, then we would have a dn after our integral. Okay, so whatever variable the function is of, you write that variable here after the d, so that we know what to integrate with respect to. It's like with derivatives. For example, if we have a function f of x, and then we differentiate to get f dash of x, we still specify that it's a function of x. And it's the same with integrals. We do that with this dx at the end. And this symbol is called the integral sign. And yeah, it's just telling us that this function is the derivative of f of x. Okay, that's the function of the integral. And it is, as an indefinite integral, the reverse process of differentiation. So how do you recognize that this is an indefinite integral? It's because there's nothing over here. If there are numbers there, that means that it's a definite integral, and since there aren't any, it's an indefinite integral. So indefinite integrals are indeed just the reverse operator of derivatives. Okay, now let's get to definite integrals. Okay. Oh, and I forgot to mention this, but the antiderivative is just the integral pretty much, but without the constant. So technically here we should add a c for constant, plus c, and that is because any constant when differentiated will just give 0. So we can add any constant and the equality will still be true. So don't forget this constant. Now, the difference between indefinite integral and antiderivative is that the antiderivative doesn't have this constant here. So for example, if you're just asked what's the derivative, the antiderivative of g of x, you just say it's f of x, not f of x plus c. But if you're asked what's the integral of g of x dx, then you have to say it's f of x plus c. Okay, so let's try a simple example. For example, what's the integral of 2x dx? Well, it's x squared plus c, because if you were to differentiate x squared, you would indeed get 2x. So the integral is like asking, what can I differentiate to get whatever's inside of here? Okay, and we add this plus c, which is a constant, because any constant differentiated will just add 0, and that maintains the equality. Okay, so that's a good example to get a good understanding of this. Now let's talk about definite integrals. Definite integrals have these boundaries over here. We call them integration boundaries or integration limits, a and b, and usually these are either numbers or parameters, okay? But let's say they're numbers. So they can be, for example, 2 and 5. Our function can be, again, 2x and then the dx. So this is the form of a definite integral. And what this means is that the integral is evaluated between 2 and 5. And this fundamental theorem of calculus that we're going to talk about now gives us a sense of what that means, okay? So when we have boundaries, that means that this thing is equal to capital F of B minus capital F of A, where B and A are just read off from the boundaries over here. And now what is capital F? Well, capital F is just the antiderivative of whatever function we have here. So to evaluate a definite integral like that with boundaries, what you have to do is first determine the capital F function, the antiderivative. So you have to determine the indefinite integral first, and then you just evaluate that integral at B, and you evaluate it at A, and then you look at their difference. And that is the answer to the problem, okay? And we can write this in more condensed form with these square brackets with the B and the A on top. So all of these three expressions are equal. They're just different ways of writing the same thing. And the fundamental theorem of calculus tells us that this is true, and that this integral is equal to the area underneath the curve between A and B. And what's the function of this curve? Well, it's just y equals f of x. Okay, and f of x is our function inside the integral. And our boundaries are A and B, which we write over here. So this integral is the shaded area. Okay, and that's why we use integrals mostly. It's to determine the area under a curve, so that's for definite integrals, between 2 points, A and B, right? That's what we use integrals for. So let's say we had the function x squared, right? X squared. And we wanted to determine the area underneath the curve between 0 and 1. How would we do it? Well, we can use an integral. Our function is x squared. We need the dx, and the integration limits are 0 and 1, because those are the points between which we want to find the area. Okay, what function can we differentiate to get x squared? How about x cubed over 3? And indeed, that works. If you differentiate this, you get x squared. And we need to maintain the integration limits, 0 and 1. And then we just apply this formula. So we have x cubed over 3 at 1 will just be 1 cubed over 3 minus 0 cubed over 3. And this is just 1/3. So 1/3 is this area here, under x squared from 0 to 1. That's how this works. Okay. And if you're wondering how I got to the fact that the integral of x squared dx is x cubed over 3, like how did I know this? It was not just a guess. There are rules, but we'll talk about those rules in another video, okay? So don't worry about that for now. We will talk about them in the future. And technically here I should have a plus c since it's an indefinite integral, but in the case before, whenever you have definite integrals, you don't have to write plus that constant, okay? All right, so that's it for today's video. Thanks for watching, and I look forward to making some more videos on integration in which we will learn all the different techniques. We have the reverse power rule, which I actually used for integrating x squared. We also have the integrals of trigonometric functions, exponential functions, logarithmic functions, U substitution, trigonometric substitution, integration by parts, and so on. And we'll cover all of them in the videos to come. So stay tuned.